In this video, I'm going to explain how to find the volume of a solid of revolution using disks, or the disk method. And in particular, we're going to derive the formula for finding the volume. So let's suppose that we have a function f that's positive on the interval a to b. So what that means is that its graph lies above the x-axis. Now, we really do need that it's positive, otherwise this problem's not going to make sense. Now let's consider the region R, this region in here, that's bounded above by f of x. It's bounded below by the x-axis. Okay, on the left by this line x equals a, on the right by the line x equals b. Okay, so we have this region R right here. Okay, and the question is, what is the volume of the solid that results when we revolve this region around the x-axis? Okay, so when this region revolves around the x-axis, it's going to sweep out a three-dimensional region. Okay, the region should look something like this. Okay, for this particular problem. And the question is, what is the volume of that solid of revolution? Okay, now what we're going to do is divide this interval from a to b up into some sub-intervals. Okay, and we'll label these points x1, x2, and so forth. Okay, I guess a would be x sub 0. B would be, I guess, x sub 5 in this problem, but we'll just say we're going to divide it up into n intervals. So it doesn't have to be 5, but let's just say n. Okay, and what we're going to do is above each of these intervals, we're going to make a rectangle. Okay, so let's say in the second interval here, the second subinterval, I'm going to pick a point. Okay, I'm going to call that point x sub 2 star since we're in the second interval here. Okay, and what we're going to do is make a rectangle that's at the height of the function there. Okay, we're going to take this rectangle and we're going to revolve it around the x-axis. Okay, so it'll revolve around to down here. Okay, so notice what we get is a disk. Okay, this becomes a disk. Okay, or a cylinder is another word for disk. Okay, and every disk or every cylinder has a radius r, and it also has a height h. Okay, now the height h of this disk, okay, remember it's a three-dimensional here. We're taking this and revolving it around the x-axis. The height of this disk is really just the width of each interval here. And we're going to call the width of each subinterval delta x. Okay, so h is just going to be delta x. Okay, and the question now is, what is the radius? Okay, the radius is just the height right here. Okay, the distance from here to here, that is the radius over here. So what is the height? Well, if this point is x sub 2 star, the height will be f of x sub 2 star, right? The value of the function there. Okay, so r is f of x sub 2 star. Okay, now let's remind ourselves what the formula is for the volume of a disk, okay, or volume of a cylinder. So the volume of a disk is equal to pi r squared h. Okay, pi r squared is really just the area of the circle here. You multiply that by h, you end up getting the volume of a cylinder, or the volume of a disk. Okay, so let's look at this particular disk here. So I'm going to call this V sub 2, okay, because it's the volume of the second disk. I didn't draw in the first disk here, or the third, or the fourth, or the fifth disks. So I'm going to call this V sub 2, volume of the second disk. It's pi times r squared, but r is f of x sub 2 star, okay, squared, and the h is just delta x. Okay, now that is just the volume of the disk. I would like to find the volume of this whole solid of revolution here. But we can think of that whole solid of revolution as just consisting of, one way to approximate the volume is by looking at a whole bunch of these disks. For example, I could draw in all 5 of these disks, okay, and find the volume of each of those 5 disks, and that would be an approximation of the volume of the solid of revolution. Okay, so total volume of disks, of course, will just be V1, so the volume of the first disk, plus V2, plus all the way on out to our last one, V sub n. Okay, in this case it would be V sub 5. Okay, but what is V sub 1, V sub 2, V sub 3, all the way up to V sub n? Well, V sub 1 will be pi times f of x sub 1 star squared times delta x. Okay, where x sub 1 star is a point in that first interval, so maybe the midpoint, let's say. Okay, plus v sub 2 star would be pi times f of x sub 2 star squared times delta x, all the way on down into the last one, which is pi times f of x sub n star squared times delta x. Okay, now we can write this in more compact form using sigma notation. Okay, this is really the sum from k equals 1 to n of pi times f of x sub k star squared times delta x. Because if you plug in 1 for k, you get this first term here. Okay, if you plug in 2 for k, you will get the second term. If you plug in all the way until when you plug in n for k, you get the last term. Okay, so this is the total volume of the disks we can write like this. Okay, now that's not the exact volume of the solid of revolution. In fact, if I only did 5 disks, maybe my approximation isn't actually a very good approximation. Okay, but what could give us a better approximation is if we used more disks. If our n were bigger. So instead of using n equals 5, if we used n equals 100, okay, we'd have more and more disks. They'd be thinner and thinner and thinner. Now, why isn't my volume exact? Well, notice I'm off a little bit right here, and I'm off a little bit right here. I have a rectangle that's straight across on the top here, but the function itself is kind of curvy. It's bendy. So that's why we're not getting the exact volume. But the more disks we have, the better. Okay, and in fact, if we take the limit as n goes to infinity, we will get the exact volume. Okay, so exact volume, okay, is going to be the limit as n goes to infinity of the sum from k equals 1 to n of pi times f of x sub k star squared times delta x. Okay, now just like before, it turns out this is actually equal to, okay, if you remember from the previous video on the definition of definite integral, this limit of a sum, okay, becomes an integral, okay, the integral from a to b. The delta x here becomes the dx. Okay, now the pi is just pi, and the f of x k star really just becomes f of x, but we still have the squared on here. Okay, and you'll notice this formula right here is the formula that I had right at the beginning. Okay, this is the formula for the volume of a solid of revolution. Okay, there's a multiply here.